My project is on varying the depth of field for superior compression in cloud rendering. If you do not understand some of the terms in the title, the first few introductory slides should clear it up for you. So don't worry and hang on. Video frames with a narrow depth of field have fewer details in the background compared to a frame with a larger depth of field. As a result, video frames with a narrow depth of field have lower video bitrate. So therefore, depth of field can be used as a mechanism to control the bitrate of the video. However, the challenge here is that varying the depth of field of a video requires knowledge about the depth of the video pixels being streamed. Now, how do we overcome this challenge? We actually don't. We work in a domain where we already have 3D information about the scene, which is cloud rendering. Cloud rendering is a paradigm where devices, such as VR headsets, offload computationally intensive task of rendering 3D scenes to edge servers, and then they receive the rendered result as streamed video frames. As the video streamer already has the 3D information of the video being streamed, depth of field can be simulated and used as a means to control the video bitrate. Before we carry on, we'll first have to verify the hypothesis that reducing the depth of field indeed reduces the file size of the resultant images and videos, and that's what we'll be doing in this section. First, we'll verify a hypothesis on rendered images. To render images at different depths of field, I have a 3D scene set up in Blender. Blender is an open source 3D modeling and animation software. The scene setup is shown on the screen. The scene is lit using an HDR environment map. The Cycles render engine on Blender is then used to render images from the scene at a given depth of field. Cycles is a physics-based path tracing engine that simulates a model of a camera with defined aperture size. The image shown here is rendered with an f-stop of 0.1, which is why the depth of field is very narrow and the background is blurred. I'll now show images with gradually increasing depth of field. As you could see, the background becomes increasingly clear as the depth of field increases. The graph here shows the relationship between the f-stop and the image size. We can see that the file size drastically increases as the f-stop increases. Perhaps the size of the image at f10 is 65% bigger than the image size at f.1. This shows that the image size indeed reduces as the depth of field decreases. In addition to images, I use Blender to render 2-second videos at different depths of field. I'll now show you a couple examples. This video was rendered at an f number of 0.1. This video is rendered at an f number of 10. Similar to images, the video sizes increase as f-stop number increases and the depth of field increases. The size of the video at an f-stop of 10 is 53% greater than the size of the same video at an f-stop of 0.1. Now, I'll be explaining the design of the cloud rendering system used in the project. I used Unity and WebRTC to build the cloud rendering system. Unity is a free software mainly used for game development. I'll shortly be showing a demo of the game, but before that, I want to talk about the component that allows us to transmit video frames over the network, which is WebRTC. WebRTC is a free and open source framework that enables real-time communication with web browsers via the use of APIs. The figure on the screen shows the setup of the cloud rendering system. Please refer to the paper for more details. Now that we have set up the cloud rendering system, it's time to evaluate the advantages of using aperture as an additional knob to control video bitrate. I'll now demo the game that I've built. The game is played on a simple video player on a web browser. The knobs to control the game are on Unity. Here I've shown two important knobs that I'll be using during the demo. The one on the left is a slider that controls the virtual camera's aperture, and the one on the right controls the video bitrate. Now let's move on to the demo. This is the Chrome web browser playing the video that is streamed by Unity after rendering. The game is simple and consists of an input-controlled fox moving through a forest. I am now increasing the camera aperture in Unity. You can see that the depth of field in the streamed video dynamically changes as a result. The Unity knobs are not seen as I'm not recording that screen. WebRTC stats show that the video bitrate can reduce by 4 times when aperture sizes increase. Surprisingly, this also leads to improvement in other quality of experience metrics, such as video jitter and delay. Please refer to the paper for more evaluation details.